Our next speaker this morning is Elena, and she is going to tell us a lot more about multi-threading support for HDF5 and new types of storage.
Okay, so first of all, I want to thank organizing committee that because my talk slightly out of the main theme, but I hope you will find it interesting and I will learn something from you. So first I will give outline. Outline is just one slide from where I came from. Actually, I came from HDF Group, but now I'm with different organization. And we'll talk about two projects that we are working right now. It's adding multi-thread access to data in HDF5 and support for sparse and variable length data in HDF5. So we're kind of thinking as a small company, what we are doing. We are not doing HDF5, but we want to make it better. So we organized the company, it was 2 years ago already, to sustain and enhance open source by adding new features that were requested by community for quite some time. And we as non-for-profit were not able to raise money. So we are funded now by Department of Energy Small Business Innovative Research Program, and we awarded grants to work on toward multi-threaded concurrency and supporting sparse data in HDF5. And I also trying to raise money to do encryption and to finish Swimmer. And with Swimmer, VFD Swimmer, it will give us also the feature of avoiding data corruption in HDF5. So if you are interested about talking data corruption, new version of Swimmer that doesn't have any restrictions on how it operates, please talk to me. So multi-threaded access to data in HDF5. What do we mean by this? We mean that we will allow concurrent threads to enter the library without corrupting data in memory and in the file. So everything should be good, because right now you cannot do it. Software was designed without thread safety in mind, and it's now 25 years old with all these features we're talking about. So is it really even feasible to do it? If we look at the calling graph of one of the tests from CGNS libraries, Computing Fluid Dynamics Code, IO library, it shows interdependence between the packages. And now I need, how do I do? If I look inside some nodes, you will see how many interdependencies going on. So is multi-threading is even possible? And because of all recent development, the answer is yes. So let's look at HDF5 architecture. So you see different layers of HDF5 in HDF software. You have applications sitting on top of the library with a layer of C APIs. Then in 1.12 release, a new layer, virtual object layer was introduced that allows to create different connectors to storage. And those connectors do not necessarily put data in HDF5 format. It can be any other format, any type of storage, and so on. So pass-through wall and terminal wall connector puts data in storage. Pass-through wall may reorganize some data. And there are many connectors written now, especially in high-performance computing space, and some of them are multi-threaded. But because we have global lock that sits here, they cannot really leverage that functionality. So what we decided to do, let's look at what may happen if we change some assumptions here. I don't know. Okay, so let's step back and look at the architecture. So what we can see that to get to the layer where the connector is, we need to push lock below wall layer. We also notice that, and we review the design in HDF5 library, it does a lot. It prepares data for I/O, but it also has a lot of different functions like dealing with object IDs, with their properties, with selections, and so on. So if, and most of the wall connectors, they use very limited number of packages. And fortunately, those packages are so-called utility packages. So if we make them multi-threaded, then we can create multi-threaded wall connector. And in our case, wall connector will do the following. It checks if I always support it because at the beginning we will not be supporting all IO operations, and it will route to the native library if it's not supported, or it will route further down through the connector, and connector will check if connector will pull out the location of the data, and those logs can be pushed to this level. So now we can allow multiple thread to enter CPI and wall layer and go through multi-threaded bypass wall connector. And then if we make also VFD layer multi-threaded, we have multi-threading to file system. So in blue on the left, you see the packages we already modified and make them multi-threaded. So it's now in testing. It was not an easy task, but at least it's possible. And we will be rewriting H5P package completely. It's not worth saving, simplifying it and making multi-threaded, and H5VL. Wall connector is almost done, at least it's prototype, so we just need to convert those packages. Question then, very rightful, we're doing still some serialization when we're talking to HDF5 library, and will it work? Will anyone get any good performance from this? And the answer, once again, yes. Last workshop at ITER, Luke Grothheinz from APFL Blue Brain project talked to me and said, listen, we even cannot read our data. What's going on? So we collaborated with him on the project. The next slides is his slides and show performance improvements that we achieved. So Blue Brain project is about digital reconstruction of mouse brain. And usually some data comes in HDF5, and HDF5 files have representative of the data sets you see here in JSON, but it really, for the reason of this talk, it doesn't matter. We created synthetic data that had represented real data, and it had about 20,000 data sets, total size 17 gigabytes, and we use page allocations from the reason you will see later with the page size 64K. So two different thread solutions were implemented. The first solution was that sequentially location of the data set raw data was found by HDF5 library, and then each thread read from that location. The second strategy was implemented, so-called page-aware solution, that instead of reading directly data, each thread reading directly data of the data set, each thread read assigned pages. Then pages were assembled in memory, and then data sets were read from memory and written to another file. So we have direct approach and page-aware approach. And this is the result. So for left side gray bars, you see just performance and runtime in seconds for that data set. For HDF5, it was version 1.13.2, which is essentially 1.14.0 release. And remember, it's page deallocation, because without page deallocated file, this time access would be logarithmic. So we even couldn't put it on the graph. So the next bars with the direct approach, you see two columns, 3 and 3. It was 3 runs performed by 12 threads. And in red, it is time that takes to read serialization, location of the data using HDF5 library. And on the right columns, right 3 columns, it is when the same locations were pre-composed and they were put in JSON file, which can be easily, you can access it in parallel. So you see reading metadata becomes no problem at all. And with page-aware, the same approach. So by this almost right column, this is the best result, and it achieved single node bandwidth of GPFS system over InfiniBand. So multi-threading, yes, it will help you with your performance problems. And this is exactly what was prototyped here is exactly the approach multi-threaded wall connector will take for now. In the future, it can be enhanced, and at some point, it will be converted to functionality of current HDF5 library, but who knows, it will take some time. So now I will talk about support of sparse and variable length data in HDF5. This is another project, and as you know, I believe Armando, like many years ago, it was like 5 or 6 years ago, he approached HDF Group to create a schema for storing sparse data. And we kind of rejected it because different people will have different schemas in memory, and then you will not have standard. So this work is addressing standard way of storing data without, regardless its representation in memory. So what is sparse data? Really, again, it comes from everywhere, anywhere, and there's no standard definition. So we need kind of say, okay, we know. In linear algebra, it's usually when the data is considered sparse if there is less than 30% of matrix elements are non-zero. And in experimental sciences, the use cases we saw, it was 1/10% to 10% of gathered data is of interest, but it may contain a bigger percentage. And use cases we look at was adaptive mesh refinement, linear algebra. There's also example of sparse data reconstruction. I didn't know it, but when we go to MRI, they take very high-speed images on very low resolution, and they use reconstruction techniques to construct high-resolution image and then go back and reconstruct high-resolution sequence. That's why sometimes you have artifact and always seek second opinion on your MRI. But the use case that drove us, it was really came from Slack. Once again, it takes time to raise money. We talked with Slack people 7 years ago or even more. And use case they had, it presented on this picture. This is the images they were getting from, they were supposed to be getting from the new LCLS that started last week, right? They have first experiments. So what Slack images have, they have very specific structures that, like, there are region of interest, rectangular region of interest that usually take less than 10% of the whole image. There also can be 50 to 100 small subsections, typically consisting of 5 of 10 contiguous points of pixel. And those number of those region of interest, their sizes, configurations, and locations, they change from image to image. And requirements for Slack was, could you please make HDF5, think how you can do it, so you will store only region of interest, and one should be always be able to recover where that region is, and the values, of course, in the region. And then every nth two-dimensional image needs to be stored as a full image. We also added some other requirements in spirit of HDF5 that we call the entries that are region of interest. Those are defined because the experiment could tell us which region of interest existed and what they wanted to write. So they know automatically those regions. And we know how we can write them down, so they're explicitly defined. And defined entries can be read back, and also we would like to have interface to this new storage that's compatible with dense data sets. So the code that designed for existing data sets will still work, reading defined values if available, and if not, there will be fill values that will fill that region. Also, ability to use filtering was important. Ability to erase defined values. For example, you gather your data and something you want to fix, you can define new regions, and you can erase current data and their locations and put new ones. And what is also very important, data is portable. It doesn't depend on data storage in memory. This set of slides has a reference slide with the pointers to RFCs that we created, design documents, and I'm really soliciting feedback on our designs. So let's look at the new storage paradigm that we call structured chunk, and the reason will be understood later why we called it this way. So in this sparse matrix, let's think that 0 may represent a value that is not defined, or if it's linear algebra, it's just a 0 value. So if we write a shown subarray using hyperslab selection, how it will be stored in the file. And currently, chunk storage is used and all elements are stored. For example, experiment produced only buffer of this gray area. HDF5 library will take the chunk, fill it with fill value, put defined elements in the right locations, and then we'll do write. Of course, compression can be applied. So with the structured chunk storage, locations and values of defined elements specified by hyperslab selection are stored in different sections of the chunk. So in section 1, we'll have encoded selection. HDF5 provides special functions to encode selection. And essentially, it is storing the coordinates of the contiguous hyperslab. So it will be corners left upper corner and lower right corner. So it will be 4 points here encoded, which is less than all zeros we have already in the chunk. And second section will be just the values. So for file format, this is kind of simplified picture of what is going on. We defined changes to file format, actually not changes, it's extension. And for fixed size elements, we just need 2 sections. We will store encoded selection of defined elements, and we add a section checksum, because if the section becomes corrupted, we will not be able to interpret the values in the section where data is stored. But for variable size data type, we need to do a little bit more work. We need to store not only data, but for example, if it's strings, we need to store lengths of the strings and offsets to the heap where the value of the string is stored. And we added checksums because, once again, if that section 1 that stores that information becomes corrupted, strings will not be found, and a variable size data heap in general may contain, for example, for nested variable length data types, more sections, so there will be pointers within that heap. So checksum is also required. And now you can notice that, first of all, section 0 is not required. You may have perfectly dense chunk or dense data set of variable length, but now what will happen? We will be able, since data is not stored in some HDF5 heap, it is stored in the chunk, we will be able to apply compression to variable length data. And we will be able to retrieve section by section. APIs will allow us to do this. But with the variable length, now we really can compress data. So programming model doesn't change. We can use, for example, when we create a sparse data, you follow through the regular steps with existing APIs. There is a new definition of sparse chunk. You create, you apply compression, and in this case, compression is applied to all sections. It's the same compression. And then we do create, and the last write statement, it is where you define your elements in the in memory space. You provide the buffer with the defined values, and file space, it's where the values should go, and you're done. So propose new APIs. We, of course, need to have API to get defined elements. It retrieves locations of those elements. You can erase, as I said. Unfortunately, for direct chunk IO, we need to introduce new functions because now chunks have more sections. But this also gives us opportunity to move filter functions, make them slightly better, and this is where feedback will be highly appreciated. Then I showed you a filter function, and what we had in the past, there were several, one complaint that buffer, which is, I believe, int in 32 in previous slide, right? Or int, it's some int. It should be really be void because sometimes filter data is more complex and cannot be fit in some integer array. Flags were changed to unsigned 64, just give it the biggest one for the sake of all connectors. And we had to add section number because you can apply now filter to the section number, and you can apply different filters to section numbers. So this is how the code will look like. You can apply, for example, deflate filter to part of the chunk that has fixed data. For example, there are integers like data string length and offsets, and apply a different compression to data with the real data of the defined values. So that's the end of my talk, and I really want to thank HDF Group developers who are talking to us and discussing our designs. And there is reference slide and now questions. So thank you.
Okay, there's a question online. Please go ahead online. I think you are muted. Please.
Hello, can you hear me?
Yes.
Thanks for your wonderful presentation. I have been working in a similar subject for the past 6 months. Have you thought about right optimized index structure for supporting sparse arrays in HDF5?
I didn't get the question.
Have you thought about using right optimized indexing structures for supporting sparse arrays in HDF5?
You mean, but this will, you mean the storage types that are used for storing sparse matrices like encoding of columns and rows?
I mean, basically that if you use a right optimized index structure, you can encode the actual values of the array similar to an index or something like that.
Right, and this is where we looked at it. We think that first of all, it's kind of not in spirit of HDF5, and you will be using several data sets to store that data. And it will not be portable in the sense that recipients of the data, they will need to know what those arrays mean. There is no good way to describe. This way, it is self-descriptive. And there are, by the way, several projects that is going on. H5 sparse is one, it's in Python that defines the schema. And there is a project from Hughes Institute. I will be talking to them soon. I didn't have a chance exactly to look what they're doing, but they're also using this high-level approach by storing encoding in different data sets.
Okay, thank you.
Mm-hmm. Thank you. Other questions?
So thank you for a very interesting talk. So it looks like that there are new impressive features should come hopefully soon. So I have a question to that feature. So if I understood correctly, would it be possible in the future to reduce the size of the file by deleting some of the chunks from dataset? So I'm viewing this possibility for the possible data reduction without rewriting the complete file.
I don't think you'll be able without rewriting to do it, because one thing definitely, when you define, currently you're using chunk storage. To store data in your way, you need to do different type of storage, meaning it has to be rewritten. Data size will decrease, but it depends on, once again, on your data. So I don't know, we can talk about it, but I don't think you'll be able to do it. It's just for future that when you really know that you have sparse data, you'll be able to save space, which may not always be true, because, for example, if your chunk is really dense populated, it will be almost a lot of overhead to store that encoded selection. So I don't know.
Yeah, from my glances, looks like rather straight away. So if you already could be able to save sparse data, then you can just delete some of the chunks. So I see only the problems in parallel processing of that file.
You can always delete data, but then you will have holes in the file. You have to repack, so it still rewrites the whole data. So let's talk and find out what you want to do. What is your line, processing line is.
Okay, thank you.
But you will save, and you will, what most important, it's portable, it's standard, and you will always find where data is located. And it's efficient because you do not need to read the whole chunk to find data location, because you can read only section, because some of that information will be stored as a metadata, and it will be easy. We can easily retrieve encoding without reading the whole big chunk, for example.
Thank you.
Okay. Any other questions? No questions online? Oh, Ed.
Hello, thanks for that great talk, Elena. I don't have a question, but I just want to say that having a multi-threaded HDF5 would be a tremendous boon to the whole community. We have had requests through the NetCDF community for multi-threading, and yeah, that is going to be great. So I urge the whole NetCDF group to really embrace that, because it's complicated. It's a real pain in many ways, but it is tremendously helpful for a lot of applications.
Thank you. And if you have now use case, because we can work on the solution that you can implement in your user space, as I showed, we implemented with Luke, and it really helped. They were able to read the data, because now, especially when there is, chunk sizes, as we know from Alexander talk, can be very weird in NetCDF data. There are many weird things that on the reader side can face.
And even setting aside the performance gains on I/O, there are applications that they want to make multi-threaded for other reasons, and this is the reason they can't.
Right.
And so just making them able to make the whole application multi-threaded would be tremendously helpful to a lot of applications.
So we hope to have a first version of the connector and packages that we need, sometimes in spring next year, if everything goes fine, because HDF5 library is unpredictable, and already H5i took much longer, but also a lot of things were learned. So we're moving, but yeah, we have 2 years for the project.
Go ahead. Sorry.
So thank you for the presentation. The both features looks very nice and promising. I would have a question concerning the presentation of the multi-threading performance in the neuroscience case, when there was this comparison left-right with metadata. Did I understand it right that it was one time it was with metadata in HDF5 and one time in JSON, and I could interpret it. You said, okay, you can save them in JSON, that it is fast, but can I interpret it like that keeping the metadata, if there are many, in HDF5 and reading them is a performance bottleneck?
You may, sorry, maybe misheard, leaving metadata in memory, right?
Like I mean that when I see that like the third set of columns, when the long times for metadata are in red, and what does it mean? Like this is like if I keep a lot of if I'm reading metadata during processing, from HDF5, it is slower than when I'm reading from JSON.
So if you're reading metadata from file, from storage, this is how it will slow. This is overhead you have. I don't remember, Luke, correct me, I believe he was reading metadata in JSON file that was also in storage, but it can be parallelized because multiple thread can read that file. But to read through HDF5 library, multiple threads still cannot enter HDF5 library in concurrent. But what it hints you to use really very clever page allocation, because you can allocate metadata in pages and have big enough page buffer and metadata cache to keep almost all your metadata in memory. And then you will not have those big things because it will be reading, it still will be serialized, but it will be reading from memory. And one of optimizations that can be done playing with all those VFDs, which should be done long time ago, we have core VFD driver when all HDF5 file is brought into memory and reading is done from memory. What we should be doing also, we should have metadata core file. So all metadata from HDF5 file is in memory, and then there is really no overhead of pulling metadata. So there are room for optimization.
Okay, thank you for this options for optimizations, yeah, for suggestions. Well, I have one connected question. So we often in photon science are reading metadata from this, we call it master files, and then we read the data from detector files where are images. Yeah. Should I somehow, can I optimize having? I really don't have much metadata in this large files where I have data and I have a lot of metadata in one file. Yeah, is there any optimal approach to do such I/O?
First of all, we need to be careful when we talk of metadata. Here we're talking about HDF5 metadata, which contains information about dataset groups about HDF5 objects, right? And like data types and user-defined attributes. If it's what you're talking about, yes, and there are drivers like split driver, but it's still, the thing is that you have to have all metadata for fast access in memory for HDF5. Then library doesn't go to do small I/O because metadata pieces are very small, and this is where I/O becomes inefficient.
Okay, thank you.
Yeah, optimizations and HDF5 library should do it actually for you to minimize this. And there are several tricks you can play now, and you may try. So let's talk.
All right, thank you.
Okay, let's maybe stay on track. We have a
Right.
half an hour break now, and enjoy. Thanks again, Elena. And